Welcome dear learners, we are studying quantum chemistry and in this module we are studying the part second of the hydrogen atom problem. The content of this module are the Schrodinger wave equation for hydrogen atom problem, the r, theta and phi equations, complete solution of R equation, associated Legere polynomial, normalized wave function, first few radial wave functions and the total wave function of hydrogen atom. First of all, the Schrodinger wave equation for hydrogen atom problem. It should be noted that for systems like a hydrogen, rigid rotator, etc., it is more convenient to express the Schrodinger wave equation in spherical polar coordinate. In spherical polar coordinate, we know the fact that there are three variables, namely r variable, theta variable and the phi variable. Hence, in spherical polar coordinate system, the Schrodinger wave equation can be represented like this: 1 by r square into dou by dou r of r square dou psi by dou r plus 1 by r square sin theta into dou by dou theta sin theta into dou psi by dou theta plus 1 by r square sin square theta into dou square psi by dou phi square plus 2 mu divided by s cross into e minus vr into psi is equal to 0. Here, it should be noted that mu represents the reduced mass of the system. The three variables in Cartesian coordinate related to spherical polar coordinate by this relation. This is very familiar to us and we have discussed such things in the first part of the hydrogen atom problem. X is equal to r sin theta cos phi, y is equal to r sin theta sin phi and z is equal to r cos theta. And it should be noted that the variables r range from 0 to infinity and the value of phi is between 0 to 2 pi and the value of theta is between 0 to pi. Hence, this represents the Schrodinger equation for the hydrogen atom problem in spherical polar coordinates. Now, after the separation of variables, we got three parts of the Schrodinger wave equation, or we will get three different components of the Schrodinger wave equation, namely the R equation, theta equation and the phi equation. This separation we have carried out in the first part of the hydrogen atom problem discussion. First of all, the phi equation. This is the phi equation. Dou square phi by dou phi square plus m square phi is equal to 0. We know about the complete solution of this equation that we learned in the first part. The complete solution of the phi equation is phi of phi equal to 1 by root of 2 pi into e raised to im phi, where m represents a quantum number called magnetic quantum number. Its value is equal to 0, plus or minus 1, plus or minus 2, etc. Next, this is the theta equation. The theta equation is 1 by sin theta into d by d theta sin theta into d theta by d theta plus lambda minus m square by sin square theta into theta of theta is equal to 0. We know about the complete solution of the theta equation. The complete solution of the theta equation appears in form of a polynomial called the Legendre polynomial. And finally, we have the R equation. This is the R equation for the hydrogen atom problem, and now we are focusing on the complete solution of this R equation. The R equation for the hydrogen atom problem is 1 by r square into d by dr of r square into dr by dr plus 2 mu divided by s cross square into e minus vr into r minus lambda by small r square into capital R is equal to 0. This about the Schrodinger equation, that is R equation, and we are studying the solution of this R equation exclusively. Now, we have this R equation 1 by r square d by dr of r square dr by dr plus 2 mu by s cross square into e minus vr into r minus lambda by r square into r of r is equal to 0. To solve this equation, we have to consider two important things: the potential energy and angular momentum of the system. And now we assume that R of R is equal to chi r divided by small r, where chi r is a function of small r. And also we are taking the assumption that lambda is equal to L into L plus 1. And now we are going to substitute these two values, that is R of R is equal to chi r divided by small r and lambda is equal to L into L plus 1. We are going to substitute these two functions in this equation to get, in the R equation, to get dou square chi divided by dou R square plus 2 mu by S cross square into E minus VR minus L into L plus 1 S cross square divided by 2 mu R square into chi R is equal to 0. This equation has a form of one-dimensional Schrodinger wave equation of particle of mass mu moving in the direction of small r in a field of effective potential. The effective potential is given by the relation V effective is equal to VR. VR represents the potential energy that depends only on the variable R. So V effective is equal to VR plus L into L plus 1 S cross square divided by 2 mu R square. And we have the value of VR, that is the potential energy that depends on the variable small r, that is VR. VR is equal to minus Zd square divided by small r, where Z represents atomic number, Zd represents the nuclear charge and small e represents charge of the electron. And we get, on putting the value of VR in the R equation, we will get the R equation in this form. The new R equation is like this: 1 by R square into d by dr of R square into dr by dr plus 2 mu by S cross square into E minus L into L plus 1 S cross square divided by 2 mu R square plus Zd square by R into R is equal to 0. It should be noted that this R term is R of R, because R of R is the part of the wave function that depends on small r variable. In order to solve this equation, we require two important quantities. The two important quantities we require are, one is a variable named as rho and the second one is a constant notated as lambda. And rho is equal to, rho is fixed like this, rho is equal to under root minus 8 mu e divided by S cross square. Outside the root we have also an r part. That is, rho is equal to under root minus 8 mu e divided by S cross square into r. Also, the constant term lambda is equal to Zd square divided by S cross into under root mu divided by minus 2e. Hence, we have two parameters, out of which one is a variable, that is nothing but rho, and the next one is a constant term, that is nothing but lambda. And we are now trying to incorporate this variable rho and the constant term lambda into this equation to get a new form. And on such incorporation of the value of rho and lambda in the R equation, the R equation takes the new form like this. The R equation now is d square capital R divided by d rho square plus 2 by rho into dr by d rho plus minus 1 by 4 minus L into L plus 1 divided by rho square plus lambda by rho into R of R is equal to 0. This is the modified form of the R equation. And it should be noted that this R equation has a solution in mathematics. The solution to equation 3 can be represented like this: R rho equal to e raised to minus rho by 2 into f rho, where f rho is a new function that depends on the variable rho. That is, f rho is a new function in rho. Now, incorporation of the value of f rho in the previous equation, we get a new form of R equation. The new form of R equation is like this: rho square into d square f divided by d rho square plus rho into 2 minus rho into df by d rho plus rho lambda minus L into L plus 1 minus rho into f rho is equal to 0. So our R equation now modified into equation 5 like this form. But it should be noted that the parameter f rho, that is the function that depends on rho, can be represented as a power series, or we can represent it as a summation. That means f rho is equal to summation k is equal to 0 to k is equal to infinity ak rho raised to c plus k, where ak represents some arbitrary constants and rho represents the parameter or the variable. Incorporating 6 in 5, we are getting a new equation like 7. The new equation is summation of k, ak into lambda minus 1 minus c minus k, rho raised to c plus k plus 1 plus summation k, ak c square plus 2ck, k square plus c plus k minus L square minus L into rho raised to c plus k, RHS equal to 0. This equation we get it from the summation term that we noted previously. From equation 7, on suitable modification and equating the coefficient to 0, we will get a new relation called the recursion relation. This recursion relation is very, very important. Such a kind of recursion relation we previously learned in the case of the simple harmonic oscillator. And here also such a recursion relation appears in front of you. A k plus 1 is equal to L plus k plus 1 minus lambda divided by k plus 1 into k plus 2L plus 2 into ak. This is represented as equation number 8. This relation that we obtained from previous equation, that is equation 7, is known as the recursion relation. The recursion relation allows us to determine the coefficients a1, a2, a3, etc. up to ak in terms of a0, which is quite arbitrary. A0, you are familiar with that is called Bohr's radius, radius of the first orbit of the hydrogen atom, that is theoretically 0.529 angstrom. So you are getting A1, A2, A3, etc. in terms of A0. A0 is quite arbitrary. For large values of k, we know the previous recursion relation. And this recursion relation, for large value of k, the recursion relation takes the new form ak plus 1 divided by ak is equal to 1 by k. This implies that this relation, when we put k as large quantity, it is reduced to this form, that is ak plus 1 divided by ak is equal to 1 by k. Now, when k tends to infinity, the series for f rho behaves as rho raised to L into e raised to rho. We have already this relation r rho is equal to e raised to minus rho by 2 into f rho. And now we know f rho is equal to rho raised to L into e raised to rho. This is a special condition which happened if and only if k tends to infinity. Thus, incorporating this value f rho is equal to rho raised to L into e raised to rho, in this equation we will get r rho is equal to rho raised to L into e raised to rho by 2, and it is marked as equation number 10. And from this equation number 10, that is r rho is equal to rho raised to L into e raised to rho by 2, and the recursion relation that we learned previously, by combining the recursion relation and this new relation, we can say that for a certain value of k, say that value is marked as n dash, we can take a n dash plus 1 is equal to 0, and hence we can write L plus n dash plus 1 minus lambda is equal to 0, where n dash is equal to 0, 1, 2, 3, etc. We already have L plus n dash plus 1 minus lambda is equal to 0, where n dash is equal to 0, 1, 2, 3, etc. Now, we are defining a new quantum number n, and this new quantum number later known as the principal quantum number. And the new quantum number n is defined as n is equal to L plus n dash plus 1, that is again equal to lambda. We know the relation lambda is equal to z square divided by s cross into under root mu divided by minus 2e. And now it is assumed that lambda is equal to n. So we can say that n is equal to z square by s cross into root of mu divided by minus 2e. That equality between lambda and n enable us the determination of energy of the system. That means we are getting this relation. Now I am going to show you how we got this relation. This obtained from the equality between n and lambda. We know that lambda is equal to z square by s cross into root of mu by minus 2e. This is the relation of lambda. Lambda is equal to n. Therefore, we can take a square of the right hand side. That implies z square e raised to 4 by s cross square into taking square of the square root term, root will vanish. That is mu divided by minus 2e equal to n square. Or on cross multiplying we will get n, we will get energy of the system, that is E is equal to minus mu z square e raised to 4 divided by n square 2n square s cross square, 2n square s cross square, where n represents the principal quantum number. The value of n ranges from 1, 2, 3, etc. Since the energy value depends on the principal quantum number, we can put energy as En. For getting E1, we have to put n is equal to 1. For getting energy of the first excited level, just put n is equal to 2, like that. That is, finally we got the energy of the hydrogen atom like this. En is equal to minus mu z square e raised to 4 divided by 2 s cross square n square. Now, we have this energy relation. En is equal to minus mu z square e raised to 4 divided by 2 s cross square n square, where n is equal to 1, 2, 3, etc. It should be noted that the value of the principal quantum number n greater than or equal to L plus 1, where L is a quantum number known as azimuthal quantum number. And from this relation, we can arrive at the conclusion that L is equal to 0, 1, 2, 3, etc. up to n minus 1. The value of n determines the energy of the system. We can write this equation in a simplified form like this. En is equal to minus RH into Z square divided by n square, where Z represents the atomic number. And for hydrogen, the value of Z is equal to 1. And this constant RH, that is theoretically equal to mu e raised to 4 divided by 2 s cross square. And this constant later known as the Rydberg constant for hydrogen. That is, the value of the Rydberg constant is 1.097 into 10 raised to 7 meter inverse. We can put it in centimeter inverse also. Now, we have the R equation in this form, that is rho square into d square f divided by d rho square plus rho into 2 minus rho into df by d rho plus rho lambda minus L into L plus 1 minus rho into f rho is equal to 0. Now we are making some assumptions, and we have to take this assumption f rho, that is equal to rho raised to L into L rho. And by putting equation 15 in equation 5, we can rearrange equation 5 like this, that is rho into d square L rho divided by d rho square plus 2L plus 2 minus rho into dl rho divided by d rho plus n minus L minus 1 into L rho is equal to 0, where L rho similar to F rho is a new function that depends on the variable rho. Now, the associated Legure polynomial of the order P and degree Q minus P can be denoted as L Q raised to P of rho. And this Legure polynomial satisfies this equation rho into d square L Q raised to P divided by d rho square plus P plus 1 minus rho into dl Q raised to P divided by d rho plus Q minus P into L Q raised to P rho is equal to 0. And this equation, that is equation 17, is identical with the previous equation, that is equation 16. Equation 16 and equation 17 are identical, and this equality holds good only if L rho is equal to L n plus L raised to 2L plus 1 rho. We get the complete solution to our equation in the form of L rho or L n plus L raised to 2L plus 1 rho. And the complete solution to the R equation is RNL R is equal to n into e raised to minus rho by 2 into rho raised to L into L n plus L raised to 2L plus 1 rho. And this represents the complete solution of our equation. From this solution, it is clear that this n represents the normalization constant, and the last parameter, that is a polynomial, that polynomial is L n plus L raised to 2L plus 1 rho, and that polynomial is known as associated Legure polynomial. That means from equation 19, it is clear that the radial part of the wave function, the complete solution to the radial equation, the complete solution of the R equation is given in terms of Legure polynomial or simply associated Legure polynomial. Moreover, the solution depends on two quantum numbers. They are n and L. That's why we represent the solution as RNLR instead of R of R. N is the principal quantum number and L is the azimuthal quantum number. N have whole number values 1, 2, 3, etc. And the value of L begins from 0, 0, 1, 2, 3, etc. And the maximum possible value of L is n minus 1. That is, L is equal to 0, 1, 2, 3, etc. up to n minus 1, which is the azimuthal quantum number. Now, L n plus L raised to 2L plus 1 rho is known as the associated Legure polynomial. Legure polynomials are named after French mathematician Edmond Legure. This is the expansion of the Legure polynomial. L n plus L raised to 2L plus 1 rho is equal to summation k is equal to 0 to k is equal to n minus L minus 1 minus 1 raised to k plus 1 into n plus L factorial square rho raised to k divided by n minus L minus 1 minus k factorial into 2L plus 1 k factorial multiplied with the k factorial. This is the expansion of the associated Legure polynomial. By putting different values for n and L, we will get different values for the Legure polynomial. That means we will get first few Legure polynomials by putting different values corresponds to n and L. We have the complete solution to R equation that we learned previously. RNLR is equal to n into e raised to minus rho by 2 into rho raised to L, Ln plus L raised to 2L plus 1 rho. The normalization integral to this problem is taken here to evaluate the value of n. And the normalization integral is integral 0 to infinity. I am taking the upper limit infinity because the value of the variable R ranges from 0 to infinity. And the integral 0 to infinity RNL R square dr, that must be equal to 1. And this normalization condition yields the value of the normalization constant n. By incorporating the value of the normalization constant n as 2z by ni0 the whole raised to 3, n minus L minus 1 factorial divided by 2n into L plus 1 factorial the whole cube the whole raised to 1 by 2. We will get the entire solution of radial part of the wave function like this. That means the complete solution to the R equation is like this. RNLR is equal to minus 2z by ni0 the whole raised to 3 by 2 into n minus L minus 1 factorial divided by 2n into n plus L factorial the whole cube the entire raised to 1 by 2, e raised to minus rho by 2 rho raised to L, Ln plus L raised to 2L plus 1 rho, and this represents the complete solution of the radial part of the wave function. This solution is normalized also. And in this solution, it should be noted that A0 is called the Bohr's radius, that is the radius of the first orbit of the hydrogen atom. Now, RNLR is this one, and we can put different values for n and L to get first few hydrogen-like radial wave functions. And whenever I am putting n is equal to 1 and L is equal to 0, I got R10R. That is numerically equal to 2 into Z by A0 the whole raised to 3 by 2 into e raised to minus rho. Whenever I am putting n is equal to 2 and L is equal to 0, the relation is Z by 2A0 the whole raised to 3 by 2 into 2 minus rho into e raised to minus rho by 2. And the final relation, I have to put n is equal to 2 and L is equal to 1. That is principal quantum number is 2 and azimuthal quantum number is 1. Then we get R21R, that is equal to 1 by root 3 into Z by 2A0 the whole raised to 3 by 2 into rho into e raised to minus rho by 2, where the term rho is theoretically equal to ZR by A0. Z is the atomic number. A0 is known as the Bohr's radius and R is our variable. So these are the first few hydrogen-like radial wave functions. And the complete wave function of hydrogen is given by psi NLM R theta phi is equal to RNLR YLM theta phi, where n is equal to 1 to 3, L is equal to 0, 1 to 3, etc. up to n minus 1, and M is equal to 0, plus or minus 1, plus or minus 2, etc. up to plus or minus L. N is the principal quantum number, L is the azimuthal quantum number, and M is the magnetic quantum number. And here YLM theta phi is called angular part of the wave function. RNLR is the radial part of the wave function. This YLM theta phi is called angular part of the wave function because it depends on two variables, two angular variables. They are theta and phi. That YLM theta phi is also called spherical harmonics. Also we have RNLR is equal to minus 2Z by ni0 the whole raised to 3, n minus L minus 1 factorial divided by 2n into n plus L factorial cube the whole raised to 1 by 2 into e raised to rho by 2 rho raised to L, n plus L raised to 2L plus 1 rho. And YLM theta phi is equal to epsilon into under root 2L plus 1 L minus modulus of m factorial divided by 4 pi into L plus modulus of m factorial into PLM cos theta into e raised to Im phi. This represents the spherical harmonics, and here epsilon is equal to minus 1 raised to m if m greater than 0, and epsilon is equal to 1 if m less than or equal to 0. Thus, the complete wave function is given by psi NLM R theta phi is equal to RNLR YLM theta phi. And by putting various values for principal, azimuthal and magnetic quantum number, we will get first few hydrogen-like complete wave functions like this. Psi 1, 0, 0, that is n is equal to 1, L is equal to 0, and m is equal to 0. And that is 1 by root of 2 pi into z by a0 raised to 3 by 2 into e raised to minus rho. Whenever I am changing n from 1 to n is equal to 2, I will get psi 2 double 0, that is equal to 1 by 4 into root of 2 pi, z by a0 into raised to 3 by 2 into 2 minus rho into e raised to minus rho by 2. And finally, in psi 210, n is equal to 1, n is equal to 2, L is equal to 1, and m is equal to 0. Thus, we are getting psi 210 like this, 1 by 4 into root 2 pi, z by a0 the whole raised to 3 by 2, rho into e raised to minus rho by 2 cos theta, where rho is same, that is zr by a0. Thus, in this discussion, we have studied the case of R equation, its a complete solution, and the complete hydrogen-like wave functions, that all about the hydrogen atom problem. Wish you having a nice learning experience. Thank you.